Hi, I am Monica Gracida, and we're going to have the stream tonight about the photoelectric effect. How's everybody feeling today? Why, Alex? Where are you? Why do you feel cold? Canada, yeah, well, put a jacket on and join us in this class. Hi, Camila. Anybody else out there? Okay, we're going to start the stream. Don't forget to follow us in social media. The stream tonight is going to have the content of the photoelectric effect. We're going to review wavelength, frequency, and energy of a wave. We are going to do problems in which we calculate wavelength, frequency, and energy, and we're going to do problems about energy conversions. On past streams, we had already talked about photoelectric effect, but not about the theory. And today's focus is going to be about how to solve problems. Okay. So just a quick review what a wave is. A wave is any vibrating disturbance in which energy is transmitted. And we have the electromagnetic radiation, the emission and transmission of energy in the form of electromagnetic waves. Just a review, what would be point A? What is it called? What part of the wave is this one? Okay, what is here denoted with the letter A is the crest. Letter B is the throat, the smallest lower part of the wave. The distance from the resting point to the highest point is the amplitude. The wavelength will be the distance between one wave and the next. And frequency would be how many cycles or waves per second can be made. Okay, so we have the electromagnetic spectrum that we have seen several times during the streams of chemistry. They are organized, the waves are organized by frequency and wavelength. So the higher the frequency, the shorter the wavelength between the waves. And we have all the range of the electromagnetic spectrum in here on this chart. Okay. If we, well, in some of the problems, they're going to ask us to find out which range of the electromagnetic spectrum we're talking to. So that's why I added this graph here. Just be careful here because the previous one had the gamma rays on the right. The high frequency, it's on the right, and this one, the gamma rays are on the left. So make sure we read properly so that we don't make any mistake. I added the slides and the access denied. Okay, let me check the slides for you. Give me a second so that you can have access. I don't know why it's not working for you, but at the end of the stream, I'll make sure the slides work for everybody. Okay, so just follow along with us in the stream, and then I'll make sure the slides are working. Okay, is that okay? Oh, thank you. Okay, let's move on. Okay, so for example, if they ask us, like the formulas for wavelength and frequency are these ones. We know that the higher the frequency, the smaller the wavelength, and the other way around, the longer the wavelength, the higher the frequency. So we know that wavelength and frequency are proportional to each other. If one increases, the other decreases. And we can do this formula in which the multiplication of wavelength and frequency equals c, which is the speed of light. We have it right here. So with this, we can solve either for wavelength or for frequency. Common units of wavelength are meters or nanometers. Common units of frequency are second to the power of the -1, which is the same as hertz, and also megahertz are common units here. Let's do an example. If they ask us for the wavelength in nanometers of radiation having a frequency of 2.45 times 10 to the power of 9 hertz, and they ask us what type of electromagnetic radiation does this radiation represent. Okay, as always, I recommend you to organize your data. Organize the given and the required. They gave us the frequency and they're asking us for the wavelength and the type of electromagnetic radiation. So we're going to use the formula. We're going to substitute. Okay, we're going to do the math in our calculator and we're going to get 0.122 meters. But since they ask us for nanometers, we have to change this for nanometers. Remember that 1 meter is equivalent to 10 to the power of 9 nanometers. So by using this fraction, we can turn meters to nanometers. Any questions up to here? Okay, it's pretty simple and straightforward, right? Okay, so that once we have our values of wavelength and frequency, we can check which type of electromagnetic radiation does this represent. So we go to the values of 10 to the 9 hertz, so in here, and the wavelength of 10 to the 10 to the -1 of a meter, so here, and we are in this area. So we are on the area of radar or radio waves. Any questions on how to decide the electromagnetic radiation? You just match on the chart there, or there will give you a table with values so that you can decide which spectrum, which part of the spectrum you're located. Okay, let's try another problem. In this problem now, they're asking us for frequency. The frequency in hertz of light having a wavelength of 456 nanometers. And again, they ask us to locate the electromagnetic radiation on the spectrum. So we organize our data with given and required. Okay, now we're going to solve for wavelength, not for frequency. So now it's going to be wavelength equals the speed of light divided by wavelength. We substitute, since they gave us nanometers, the data in nanometers, and the units of the speed of light are meters per second, the first step is to change nanometers to meters using the factor of 1 meter is 1 times 10 to the 9 nanometers. Once we have meters, then we use this formula, substitute it, and then we will have the answer in seconds to the -1, which is the same as hertz. Any questions in here? Yes. C is a constant which stands for the speed of light. Since all electromagnetic radiation travels at the speed of light, that's why we can do this formula to relate wavelength and frequency. C stands for the speed of light, which is always 2.9979 times 10 to the 8 meters per second. Okay, let's move on. So now we are going to now find these values on the chart. So the wavelength in the levels of 10 to the negative 7, and hertz in the levels of 10 to the 14 hertz. So we are more or less here, and that stands for the infrared radiation. Any questions? Okay, we're going to move on. So the atomic spectrum, when you heat an element and the gas, you pass it through a prism, you will see that it will emit lights of different colors. For example, here we have the atomic spectrum for hydrogen, the atomic spectrum for helium. And in every single element of the periodic table will do its own atomic spectrum. It works as a fingerprint of the electrons. So for example, applications for these are, for example, fireworks. When you see the fireworks of certain colors, is because the gunpowder is mixed with metals and they emit certain colors. So for another example, some copper compounds emit green light when they are heated in a flame. How would you determine whether the light is of one wavelength or a mixture of two or more wavelengths? If you, I don't know if you have done this in the lab yet, but if you burn copper compounds like with alcohol, you will see a green light appearing. So how do you know if it's a mixture of one wavelength or two? Who can answer to this question? What would you need to divide or to split the light into wavelengths? Okay, you will need to watch the light formed by burning copper through a prism, and then you should see if it's copper, you will see more than one line. Okay, so you will use a prism to separate the lights of different wavelengths, and that's how you can tell. Okay, another problem related to the atomic spectrum, another thing that we can solve, it's explain how astronomers are able to tell which elements are present in distant stars by analyzing the electromagnetic radiation emitted by the stars. So what they can do is compare the electromagnetic radiation with known elements here on Earth, and then they can match those elements with distant stars, and that's a way to know the elements that are being emitted on the stars. Any questions? Okay. We're going to explain a little bit about Planck's quantum theory. So in the 1900s, while Max Planck was analyzing data on radiation emitted by solids heated to various temperatures, he discovered that atoms and molecules emit energy only on a certain discrete quantities, or also called quanta. He said that atoms and molecules could emit or absorb energy only in discrete quantities, like small packages or bundles. Planck gave the name quantum to the smallest quantity of energy that could be emitted or absorbed in the form of electromagnetic radiation. So, according to this theory, Planck said that energy is always emitted in multiples of hv, where h is Planck's constant, 6.626 times 10 to the negative 34 joules per second, and v is the frequency of light. Okay, also we have the photoelectric effect. 5 years after Planck presented his quantum theory, Albert Einstein used this theory to solve another mystery for physics, the photoelectric effect. Scientists were noticing that electrons are ejected from the surface of certain metals that are exposed to light of at least a certain minimum frequency, called the threshold frequency. They noticed that the number of electrons ejected was proportional to the intensity of light, but that the energies of the ejected electrons were not proportional to the intensity. And they also noticed that below the threshold frequency, no electrons were ejected, no matter how intense the light was. So Einstein suggested that the beam of light is really a stream of particles. These particles of light, he called them, well, they're now known as photons. So using the Planck's quantum theory of radiation, Einstein deduced that each photon must possess the energy given by the equation, the same equation as the Planck's quantum theory, but now specifically for a proton. So the energy, for a photon. The energy of a photon is going to be Planck's constant times the frequency of light. So these are the observations about the photoelectric effect that Einstein concluded. Studies in which the frequency of light is varied show that no electrons are emitted by a given metal below a specific threshold frequency. For light with frequencies lower than the threshold frequencies, no electrons are emitted, regardless of the intensity of light. For light with frequencies greater than the threshold frequency, the number of electrons increases with the intensity of light. And for light with frequency greater than the threshold frequency, the kinetic energy of the electrons emitted increases linearly with the frequency of light. So using all this theory, now we have these formulas for wavelength and frequency are the same that we did before, but now we're going to add the quantum theory of Planck, and we are going to use the one that Einstein did for the photoelectric effect, where the energy of a photon is equal to the same as above, Planck's constant and the wavelength. And we can also use it to calculate the kinetic energy of the ejected electrons and the work function. Work function is a measure of how strongly the electrons are held in metals. Okay, so let's try some problems with these new equations. Okay, this is one problem. Let's take a look at it. It says it takes 7.21 times 10 to the negative 19 joules of energy to remove an electron from an iron atom. What's the maximum wavelength of light that can do this? So we organize our data. Which formulas are we going to use? We can use this one first to change joules. Right, we're going to solve for frequency here, and we're going to use the energy given divided by Planck's constant to get the wavelength, and to get the frequency, and then we're going to use the formula of wavelength equals the speed of light divided by frequency to get the wavelength, and that's our answer. Any questions on how to solve this problem? Excellent. Welcome, Santiago. Okay, so yes, example 5. Let's go to another example. We have this other example. The blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency of about 7.5 times 10 to the 14 hertz. They're asking us to calculate the wavelength in nanometers associated with this radiation and also the energy in joules of a single photon associated with this frequency. So the first thing that we're going to do is, well, organize our data, of course. And then we are going to use the formula of wavelength equals the speed of light divided by frequency. We're going to substitute the values, and we have the wavelength in meters. Then we need to change to nanometers with the factor of 10 to the power of 9. And we have now our answer in nanometers. So we are already done with number 2. Another thing that you have to be careful is the significant figures. In the given, they give us 2 significant figures, so we need to answer with 2 significant figures. Okay, for letter B, we're going to use the formula of energy of the photon equals the wavelength, the Planck's constant times frequency. So we're going to substitute, and we have that the energy of a photon is 5 times 10 to the negative 19 joules. Remember 2 sig figs. Any questions up to here? Okay, let's move on. So another example. They can also give us the energy in kilojoules per mole. For example, here, they're asking us for the wavelength in nanometers of radiation that has an energy content of 1.0 times 10 to the power of 3 kilojoules per mole. Okay, so we organize our data. We are going to use this formula. The formula is of the quantum theory. So first, we are going to change our data of kilojoules per mole to joules, because that's what we're going to need for using Planck's constant. And to change this, we need to remember from previous knowledge that 1 mole it means 6.02 times 10 to the 6.022 times 10 to the power of 23 particles. Whichever particles, in this case, they are radiation or waves. And then we're going to use the factor to get rid of kilojoules and get joules. So with this first ratio, we're going to cancel moles. And then with the second one, we cancel kilojoules, and we end up with joules. Any questions on how to do this process? Okay, once we change kilojoules per mole to joules, okay, Stephen, this is the, every mole, remember that mole, it's a unit of quantity in chemistry. Something that we're familiar with is, for example, a dozen. A dozen, it's 12, right? 12, whatever. So if we have a dozen eggs, we will have 12 eggs. If we have a dozen grapes, we will have 12 grapes. In chemistry, the unit of quantity, it's a mole. And for mole, 1 mole equals 6.02 times 10 to the 23 of whatever things we're talking to. That's the equivalence. So since we have kilojoules per mole and we want to get rid of mole, we have to multiply times the ratio of 1 mole to this constant, 6.022 times 10 to the 23 particles. That's how many things make up a mole. Just like dozen, 12 things make a dozen. Okay, Steven? Okay, don't worry. You will get to the mole when you see the next unit. When you get to stoichiometry, that's when you're using the moles a lot. But it's just a unit of chemistry that measures quantity. Okay, so you'll be fine. It's always this number. 1 mole, it's always this number. Just like a dozen, it's always 12. Okay, so by using this ratio here, as I said before, you cancel moles. then you cancel kilojoules, and it's a way to get joules per particle. And then once we have joules, now we can use the formula, solve for frequency. Frequency will be equal to the energy divided by Planck's constant. We substitute the values, and we're going to get 2.5 times 10 to the 15 seconds to the negative 1. This is wavelength. I'm sorry, this is frequency. So we need to change frequency to wavelength using now this formula. So now we get the speed of light divided by the frequency that we got above, and now we got the wavelength in meters. Again, we must multiply times the factor of 10 to the power of 9 to change meters to nanometers. And as I mentioned already, we have to be aware of the sig figs. So we need 2 sig figs on our final answer. Any questions here? Okay, excellent. We're going to move on. So let's do another example. In this example, it says when light of frequency equal to 2.11 times 10 to the power of 15, second to the negative 1, shines on the surface of gold metal, the kinetic energy of ejected electrons is found to be 5.83 times 10 to the power of negative 19 joules. What is the work function of gold? So now, this is our given and required. Now we're going to use this formula, and we're going to solve for work. So we solve for work, and it's going to be the this factor of Planck's constant times wavelength, times frequency. I always get these ones confused. Planck's constant times frequency minus the kinetic energy. So now we substitute Planck's constant, frequency, and then we subtract the kinetic energy that was given, and this is the work function of gold. So remember that the work function means how much energy we need to remove to start pulling out electrons, in this case of gold. Any questions here? Okay, so another example. X-rays have a wavelength on the order of 1.0 times 10 to the negative 10 meters. AM radio waves have wavelengths on the order of 1.0 times 10 to the power of 4 meters. Consider that the bond energy of a carbon-to-carbon bond found in organic compounds is 347 kilojoules per mole. The question is, would X-rays or radio waves be able to disrupt organic compounds by breaking carbon-to-carbon single bonds? So what are we going to do? This is our given. So we need to start, we have to compare the energy of radio waves and X-rays to the energy in the carbon-to-carbon single bonds. So we need to figure out a way of changing the wavelength into energy. So these are the formulas that we're going to use. So to be able to get energy, we need the Planck's constant and frequency. So the first step is to change wavelength into frequency using this formula. So we change, we solve for frequency for X-rays. And now we can place it on the formula. But now careful, because the answer that we have so far is going to be joules per X-ray. And we need to compare to kilojoules per mole. So the next step is to use this Okay, we're going to multiply the X-ray, the units of joules per X-ray, times again the factor of 6.022 times 10 to the power of 23 X-rays, because that's how many units we need for 1 mole. And then we're going to use the factor of 1 kilojoule per 1,000 joules. And by multiplying these factors, we can change the units of joules per X-ray to kilojoules per mole. Is this last step understood? Okay, excellent. So we're adding the factor of the changing X-rays to moles and the factor of changing joules to kilojoules. Now that we have kilojoules per mole, then it's easy to compare to the carbon and carbon single bonds energy. So since we noticed that the energy emitted with X-rays of kilojoules per mole is much, much larger than the energy on the carbon to carbon single bonds, we can conclude that X-rays will be able to disrupt organic compounds by breaking carbon to carbon single bonds. Okay, then we have to do the same for AM radio waves. So if we do the same for AM radio waves, we are going to get a value of 1.2 times 10 to the power of 8 kilojoules per mole. We use the same process, but now with the values of AM radio waves. So when we compare, now this one is much, much smaller than the energy needed to break a carbon-to-carbon bond. So AM radio waves will not be able to disrupt organic compounds by breaking carbon-to-carbon single bonds. So the final conclusion would be that X-rays will be able to disrupt organic compounds, but AM radio waves will not. Any questions on how to work out these problems? Okay. Any questions of any topic about this stream? How do you feel in this topic? In a level of 1 to 5. 1 being I have no idea what this teacher is talking about, and 5 but would be like I could totally teach this to my peers. I could go tomorrow in class and show this content to other students. Where are you now? Give me a rate. I understand the concept. Okay. Okay, Santiago, I'm sure in your book, in your chemistry book, you have plenty of problems. Remember that most books have solved problems, and you have okay, 2.5. Excellent. That's excellent, Steven. So just keep practicing and you'll have this. So that's all from my part. If you have any questions or you get stuck by solving a problem, don't hesitate to contact me. You can send me an email and I can walk you through the problems. In a moment, I will upload the replay and I'll make sure the slides are able for you to access. Any questions? Correct, Stephen. Let's go back to our data, to our answers. So once we change the wavelength to kilojoules per mole of every single ray for X-rays and for radio waves, then we are going to compare X-rays. As you can see, it's much, much higher value of energy. So of course it would be able, it is bigger than the energy needed to break the carbon to carbon single bonds, which all organic compounds have. So if you're exposed to a lot of X-rays, you can alter, you can disrupt organic compounds. And remember that we are organic compounds. Our tissue, our muscles is made of organic compounds. So that's why you need to be careful. That's why the persons that work on X-rays, they go to the back of a room which is protected by concrete walls to not be exposed for X-rays that much. So X-rays, yes, are dangerous because they're able to break the carbon to carbon single bonds. But if we do the one of radio waves, this is so low energy compared to the one needed to break the bond. So radio waves won't affect us. We're safe in the presence of radio waves, but we're not safe in the presence of X-rays. Is that better, Stephen? Did I answer your question? Excellent. Okay, do we have any other question about the stream? Let's quickly review the formulas. Okay, so I think these would be the formulas that you will be using in all this topic. So just be careful with the units, make sure you get the proper ratios. Don't forget if a mole it's in the problem, make sure, remember the ratio of 6.022 times 10 to the power of 23. And that's it. You'll be fine. Okay, so that's it from my part. And again, if you struggle with a problem, don't hesitate to contact me. I can help you solve it if you have any problems with this content. Okay, so that's all from my part. Bye, see you next stream. Thank you all for your attention.